Have you ever played with a pendulum toy or watched an old clock swing its pendulum back and forth? What's fascinating is, though the bob swings up and down, it never seems to lose energy, at least not instantly. That's the magic of energy conservation in motion. A simple pendulum, as you know, consists of a bob suspended by a string from a fixed point. When displaced and released, it swings in an arc. But what's really happening is a continuous transformation from potential energy at the top to kinetic energy at the bottom and back again. The principle that governs this motion is the law of conservation of mechanical energy. It says the total mechanical energy of the system, that is, the sum of kinetic and potential energy, remains constant in the absence of external forces like air friction. This simple device becomes a perfect example of how energy changes form while staying conserved. Let's now look at energy at three crucial points of the pendulum's swing. At the lowest point, we say the height is zero. So potential energy is zero, and kinetic energy is at its maximum. The entire mechanical energy is kinetic here. At the highest points, either to the left or right, the pendulum reaches its maximum height. Here, potential energy is at its peak, equal to m into g into h, and kinetic energy is zero. At the midway point, or any intermediate position, both energies coexist. Part of the potential energy has been converted to kinetic, and together they still sum up to the total energy, which remains m into g into h. This dance between height and speed perfectly demonstrates conservation in action. Let's explore how energy transfers during the motion of a swinging pendulum. When the bob is pulled to one side and released, it begins to swing under the influence of gravity. As it swings, energy constantly transforms between potential and kinetic forms. At the extreme position A, the bob is at its highest point. Here, it possesses maximum potential energy, calculated using the formula Pe equals m into g into h. At this point, its speed is zero, so Ke equals zero. As the bob moves downward toward the mean position B, the height decreases. This causes its potential energy to decrease, while its kinetic energy increases. The bob accelerates due to gravity and gains speed. At the lowest point B, the bob is at its fastest. So here, it has maximum kinetic energy, given by Ke equals m into g into h, and Pe equals zero since it's at the lowest vertical height. Then, the motion reverses. The bob rises toward the opposite extreme point C. As it climbs, kinetic energy decreases and potential energy increases again. At C, just like at point A, the bob again has maximum potential energy and zero kinetic energy. This entire process is a perfect example of energy conservation in motion. Energy simply shifts between forms, but is never lost. Let's now use a bit of math to calculate the speed of the bob at the mean position. When the bob falls from height h, its potential energy, m into g into h, becomes kinetic energy. So we set m into g into h equal to 1 by 2 into m into v squared. Cancel n from both sides and solve for v. We get v equals the square root of open bracket 2 into g into h, close bracket. This means the speed at the mean position depends directly on the height it was released from. Let's take a moment to understand how things differ in the real world, especially when it comes to energy losses. In theory, we say that mechanical energy is conserved during a pendulum swing. But in real life, that's not entirely true. As the bob moves through air, it faces air resistance and internal friction at the pivot and within the string. These forces cause some of the kinetic energy to convert into heat. As a result, the bob gradually slows down, and its swings become smaller over time. So even though we start with potential energy converting perfectly into kinetic energy and back, in real conditions, total mechanical energy isn't strictly constant. Some energy is always being lost to the environment. The law of conservation of energy is absolutely valid, but it applies most accurately in ideal or vacuum conditions, not in everyday setups. In reality, the energy is not destroyed, It's just transformed into other forms like heat or sound, which spread out and become difficult to recover. So yes, energy is conserved, but it doesn't always stay in a useful mechanical form. Let's try a quick problem. A pendulum bob has a mass of 200 grams and is raised to a height of 0.8 meters. What's the speed at the mean position? We use our formula, V equals square root of open bracket 2 into G into H close bracket. Substituting, V equals square root of open bracket 2 into 9.8 into 0.8 close bracket. That's square root of 15.68, which is roughly 3.96 meters per second. So, at its lowest point, the bob is zipping through at 3.96 meters per second. Let's quickly wrap up what we've learned about the pendulum and energy conservation. The simple pendulum is an excellent example of how energy transforms between potential and kinetic forms during motion. Thanks to the law of conservation of energy, we know that in ideal conditions, with no air resistance or friction, the total mechanical energy stays constant throughout the swing. But in real-world situations, friction and air resistance cause some energy to be lost as heat or sound. Even then, energy isn't destroyed, it's just converted into different forms. We also saw the important formula, V equals square root of open bracket 2 multiplied by G multiplied by H close bracket. This links the height of the pendulum to its velocity at the lowest point, a powerful connection between position and motion. And finally, pendulums aren't just textbook examples. They have real applications, from clocks and seismographs to timekeeping and the study of oscillatory motion in science and engineering.